And good morning. I'm Blake Allingham and thank you for joining into my presentation on per and polyfluoroalkyl substance removal in stormwater by radial flow treatment technology. This study was undertaken with Dr. James McDonald, Senior Research Fellow at the University of New South Wales in the Water Research Centre. Per and polyfluoroalkyl substances, known as PFAS, are a group of persistent organic compounds developed in the early 1940s. PFAS have been used in a range of industries from waterproof clothing, non-stick cookware, and aqueous film-forming foams. During the manufacturing process and consumer use of these products, PFAS is polluted into the surrounding environment. These substances bioaccumulate in the environment due to their strong carbon-fluorine bond, making PFAS extremely stable. PFAS molecules are absorbed into the human body and other biota as they are mistaken for natural fatty acids. Ultra-high performance liquid chromatography in conjunction with tandem mass spectrometry was used to analyze the samples during this study. Internal standards are added to the samples to correct for any loss during the sample preparation. The internal standards are isotope-labeled copies of the target PFAS analytes. The solid phase extraction is the cleanup step and 1,000-fold concentration of the samples as seen in the right figure. Analytes are extracted from 1 liter samples onto the solid phase extraction cartridges. These samples are then eluted with solvent and evaporated to 1 milliliter prior to analysis by ultra-high performance liquid chromatography with tandem mass spectrometry. Ultra-high performance liquid chromatography with tandem mass spectrometry is a highly sensitive and selective analytical method. 2 precursor product ion pairs are monitored for each PFAS analyte to ensure correct identification. Isotope-labeled internal standards correct for analyte loss during the sample preparation. Blank and spiked recovery samples are run to verify performance with no PFAS in the blank samples and recovery samples with known concentrations of PFAS analytes within 20% of the expected values. Duplicate samples provide further quality assurance and quality control. The figure on the left shows the ultra-high performance liquid chromatography and tandem mass spectrometry equipment. The figure on the right shows the chromatogram for PFOA and the internal standards along with the calibration curve. 48 contaminated sites are currently under investigation by the New South Wales Environment Protection Authority. They have a historic use of aqueous film-forming foams to aid with firefighting, mainly being airports, military bases, and fire and rescue training facilities. These sites and surrounding areas are regularly monitored through soil and groundwater samples. Radial flow treatment technology is commonly applied for the treatment of stormwater, utilizing 1 or more media types to capture and absorb pollutants such as total suspended solids, hydrocarbons, nutrients, metals, and other less common pollutants. Ocean Protect has begun to develop a new treatment method that utilizes existing best method practices for stormwater with media suited for treating PFAS. By adapting the media inside Ocean Protect's radial flow treatment technology to target PFAS, we aim to treat contaminated stormwater down to the Australian Drinking Water Guidelines of 2011. As part of the Heads of EPA Australia and New Zealand's National Environment Management Plan for PFAS, these drinking water guidelines are referenced for the allowed leachable concentration of PFOA and the sum of PFOS and PFHXS in unlined landfills. Phase 1 of the research project was to identify the best performing media in terms of removal efficiency at different flow rates. This was completed using a 1/24th scale of the radial flow treatment technology. Influent water was diluted to 1 microgram per litre of total PFAS using contaminated water from the field study location. This water was pumped through the bench scale test over 30 minutes with 6 150 ml aliquots taken every 5 minutes for the influent and effluent water. We selected 5 granular activated carbons and 1 ion exchange resin based on a review of absorption of PFAS onto different media types by Zhang 2019. Of these 6 media, Activated carbon number 5 and ion exchange resin number 1 provided sufficient results to be trialled in Phase 2 of the project. Phase 2 of the project was to pump water diluted to 1 microgram per litre of total PFAS at a design flow rate of 44.64 litres per minute per metre squared from our test site in Greater Western Sydney, New South Wales that has a historic use of aqueous film forming foams. Taking an influent and effluent water sample every 200 bed volumes, equating to 14,000 litres that passed through the radial flow treatment technology, allowed us to determine the loading capacity of PFAS onto the media. Samples up to 3,600 bed volumes have been analysed and show significant sustained reduction in total PFAS concentration, with an average influent and effluent concentration for total PFAS of 1.441 and 0.241 micrograms per litre respectively. The performance was not as substantial as the bench scale test. However, the controlled field scale study does not have the same ideal conditions that were present in the laboratory setting. The sum of PFHXS and PFAS had an average influent and effluent concentration over the duration of the study of 1.03 and 0.143 micrograms per litre respectively, and a median concentration for the influent of 0.971 and 0.114 micrograms per litre for the effluent. The influent PFOA concentration of the dam was not above the Australian Drinking Water Guidelines. However, continued removal occurred across the 3,600 bed volumes of treated water for PFOA. The sample at 3,400 bed volumes appears to be an outlier, with the effluent concentration 9 times above the average effluent concentration across all other samples. In addition, the performance resumes at similar removal efficiencies at the sample 3,600 bed volumes to prior results. Continued monitoring of further bed volumes will determine if this was a breakthrough of PFOA or an outlier sample. In conclusion, the radial flow treatment technology has proven it is a viable option in treating PFAS-contaminated stormwater, and with further research being conducted, a greater understanding of the AC5's media's longevity will be established. The radial flow treatment technology can be scaled by connecting in parallel to treat higher flow rates depending on site-specific details. As technologies like the RFTT are adapted to remove emerging contaminants at the source, they will minimize the impact these contaminants have on the surrounding environment and human life. Further research and evidence outside the scope of this study has indicated linking the RFTTs in series so that the runoff water passes through 2 RFTTs will meet the target outlined in the research objectives at this average influent concentration. By linking the radial flow treatment technologies in series, this will also increase the system's ability to treat higher concentrations of PFAS utilizing the activated carbon media number 5 down to the Australian Drinking Water Guidelines. Further investigation needs to be completed to determine the long-term performance of the ion exchange resin number 1. Finally, the system will need to be permanently installed onto a test site and monitored during rainfall events. In conclusion, this research has shown positive results. Thank you for your time, and if you have any questions, please ask them now or contact me with the details on the screen.